So, let us briefly review the Monte Carlo technique that we are learning here, and we will introduce what is called as an importance sampling. This is a very important development in the distribution of the random numbers, which would eventually give a very accurate, much more accurate estimate of the integral that we are attempting to compute. In summary, Monte Carlo is the art of approximating an expectation value, or we also can call it an expected value, as we were calling during our discussion, by the sample mean of a function of simulated random variables. So, instead of choosing grids of a definite width, we actually choose random numbers. So, say we need to integrate a function like this, and so this is f of x as a function of x. So, instead of doing such grading, which we have done for these known integration techniques, here we sort of and so on. So, here we choose random points on this f of x, which is the curve here, and then calculate it from its sample mean. So, these random points are taken from some distributions. It could be uniform distribution, or it could be a Gaussian distribution or a normal distribution, and we actually calculate the value of the functions at those points and take a mean of that, and that is the expected value, or rather the value of the integral. So, this is the main idea behind the Monte Carlo. So, let us look at what random sampling is, or rather importance sampling is. But before that, let us do another one. We will come back to this in a while, but let us remind you that the standard deviation or the variance of the MC technique is given by this sigma equal to root over variance of these f of x, and divided by the root over n, where n is the number of sampling points that we have drawn from a random distribution. And we know the the merits of the Monte Carlo technique. It is free from the curse of dimensionality, so that if you go from one dimension to dimension equal to 1 to dimension equal to 2 or dimension equal to 3 and so on, it really does not hurt the usage of it or applications of it. And of course, as we have said earlier, that our sole idea is to reduce the variance, and if we reduce the variance, then we get more and more accurate values. And for that, two things can be done. Either we increase the numerator, in which sigma gets decreased. So, increasing the numerator means that increase the number of sample points. Now, this is something that the experience says that the convergence is very slow. So, if you increase n from 10 to the power 6 to 10 to the power 8 or 10 to the power 9, that is the number of sampling points that you have chosen from a random distribution, then the convergence or the accuracy, improvement of accuracy is not all that much. Whereas, if we can reduce the variance, that is decrease the denominator, then sigma will decrease as well, and this seemed to be a more effective way of tackling the problem, and this is what we want to understand. And these techniques for which we increase the accuracy is called as a variation or variance reduction or reducing techniques. Okay. And the technique, this particular has a number of techniques there, and we will talk about mainly two of them. one being what is called as the stratified sampling, and importantly what we will learn is that what is called as the importance sampling. And in fact, the importance sampling is the more important of these two, and we will discuss it with a little more elaborately. But let us also look at the stratified sampling and understand that how it works. We will come back to this the importance sampling. So, what is this? So, this technique divides the full integration range into various subspaces. So, the final result is the sum of all partial results. Okay. So, how this works is that, so we divide the integration domain, let us call it R, into say k regions. So, namely let us call them as R I equal to, so this is these are R I where I runs from 1 to k. So, then the expected value in literature this is often called as the expectation value or just the expectation. Okay. This mean the same thing. The expected value is written as this E and then f of x, which is equal to over this space f x with a probability density function p of x. And now, since we have broken it down into k regions, for evaluating the integral we will have to sum over these k regions, it is not n, sorry about that. So, this is k, and then we integrate over a single jth block or jth subspace, and then you sum over all the subspaces. Okay. So, this is so the Monte Carlo estimate, we call it just MC. So, MC estimate of the expectation becomes I equal to j equal to 1 to k volume of the jth subspace. This Nj is the number of sampling points in the jth subspace, and then I equal to 1 to j f of x I. Okay. So, that is the Monte Carlo estimate of this integral, which in addition to the f of x I from I equal to, so this is n j rather. So, from I equal to 1 to some n, you also need to have another summation the over this all these subspaces where the number of subspaces go from 1 to k. So, the entire region R is actually broken into k subspaces. So, just to remind you that Nj is the number of MC points used for the integration purpose on Rj. So, on these Rj, and the volume R j is the volume of the subspace R j. So, this looks simple because it just gets extended from one region, or I mean the entire region being considered with the same probability density function. From that we go to k such regions, which the entire region of integration is broken into k of them, and then doing the procedure, repeating the procedure for all of them, and then taking the sum of all these subspaces. So, if we claim that this is any advantage over the crude or the simple MC estimate that we have done, then we have to convince ourselves from calculating the variance. And so, the MC variance is so, it is a sigma square equal to sum over j equal to 1 to k, and a volume of R j, and so this is a square divided by n j, and then the variance of this R jth subspace and this f of x. So, where this variance of this R jth subspace for the function, the integrand in fact it is equal to 1 by volume of the R j, and then of course, the usual variance that we talk about, 1 minus volume of R j, and then you have a f x p x dx whole square. So, this is integral over R j and square, and then of course, we have a p x dx. Okay. Slightly longish expression, but it just says that this is how the MC variance is calculated in this stratified sampling technique. And so, if you select carefully the number of points, then this can lead to a lower variance than the simple minded MC that we have seen earlier. So, we will write that by selecting carefully the number of points this can lead to lower variance compared to the, we have used this word earlier, crude or simple MC estimate. All right. So, the next technique that we are going to consider is called as the importance sampling. Let us go back to our slide which is there. So, this importance sampling is really believing that not always you have a unique probability density function would give you an accurate estimate. So, in some cases you could have a better probability density function which gives a better estimate. They could be proportional to each other, or they could be different than each other, but we will have to make sure that that gives you a sort of better estimate of the integral. So, if I am trying to sort of understand what is this importance weight, let us see this old problem that we have done. So, we have a circle, consider this a circle completely inscribed. It is hard for me to draw this, but let me see if I can. So, we wanted to find out the area of this circle, or in other words you say that you want to find out the value of pi, and the same thing, because this is equal to 1 unit and this is equal to 2 units. So, then that the area of this is equal to pi r square, where r equal to 1. So, it becomes equal to pi. So, the area of the circle is equal to pi. So, if you can calculate by using the MC technique, and we have thrown points at random, let me show it. So, these are points at random thrown, which are inside the circle, which have fallen inside the circle. So, all these points that satisfy x I square plus y I square is less than equal to 1. Okay. So, these are the points, and then also consider these blue points, say for example, which have not been into the circle. So, these points are not important points for us, because these points do not contribute to the either the computation of pi or the area of the circle. So, for us the important ones, or the important trials rather, the important trials are the red ones. And so, if there is a way for us to assign appropriate weight to some of the points, that is the red points here, and actually assign very little importance to the blue points, then we would do this thing much easier, or they will be much more accurate if we know how to exclude these blue points from the red points being the important points. All right. So, this is the main idea of this importance sampling. So, the methods that we have introduced so far, they generate arbitrary points from a distribution, and these arbitrary points, why we are saying, because they are from a they are random points from a given distribution to approximate the integrals. So, we have approximated the integrals by simply writing down that this is 1 over n sum over this f of x I, and I equal to 1 to n. N is the number of sampling points, f x I is the value of the function at all those sampling points. You sum all of them up divided by the number of sampling points. This is equal to the integral, and basically what you have to do is that you have to integrate f of x dx from some lower limit to some upper limit. So, this is what we have done, but so these are arbitrary points from a distribution to approximate the integrals. Okay. And in many of the cases, okay, the points, these points, they correspond to the ones that are at the value of the function under consideration, where the values are close to 0. Okay. So, we are really talking of the blue points, which do not contribute to the computation of pi or the area of the circle. So, if the value of the function at those random points, many of them would be there if we are choosing at random without really looking at the nature of the function, then we will be wasting our computational resources and our time. Okay. So, if the value of the functions are close to 0, then those things will not be, should not be considered in the sampling of the points in order to do the integral. So, because they contribute very little to the approximation to this approximation. So, in many cases the integral comes with a given density, which we called as the probability density function or the PDF. Okay. However, there will be cases where another distribution, okay, you have to carefully choose it, that another distribution gives a better fit to the integral, which means gives you a more accurate estimate of the integral, and we have to look for these another distribution, and this another distribution is what is done in the importance sampling. So, this another distribution is more important, is the important distribution which provides a better estimate of the integral. Let us see how to go about, and then we will give an example which will make things clearer. So, what we have said is that the PDF, the probability density function P of x, may not be the best PDF. for a MC integration. So, what it really means, what is meant by a best is that, so this PDF may not minimize the Monte Carlo variance. Okay. And in which case we want to use a different PDF and perhaps simpler call it QX, from which we can draw samples. Okay. So, this QX is called as the importance density or importance density function. Okay. So, this is an important thing, and how do we find QX is a matter of choice, and one has to really understand the behavior or the properties of the function that we want to integrate. We will see that. So, we can write E of y, or the expected value of the function, which is E as f x. So, that is, we know that between two limits, lower and upper limits a and b, is written as f x p x d x. So, p x is our the probability density function. So, this is equal to, we simply rearrange things here. So, we write it as a p x and a q x and a q x and a d x. Okay. So, if you see this, if you now call this as your new, and in bracket, which is, we believe that this is the important or density function or importance, as we said earlier, density function, then this is nothing but, so this is equal to the expected value of f x p x divided by q x and so on, okay, and which is weighted by this q x. So, we have simply introduced this q x distribution, and this it becomes the expected value of that of this quantity, which is f x p x by q x, which is weighted by the q x. So, thus by generating n samples, which are from this xi from q x for I equal to 1 to n, the estimate of the integral becomes I equal to 1 over n sum over I equal to 1 to n f of x I p of x I divided by q of x I, and this is called as or written as I equal to 1 to n, and we write w, which is called as the importance weights, it is written with a small w, and f of x I. Okay. And where w of well, you will have to make sure that this is written as so this w of x I, that is a smaller w. So, this is p x I divided by q x I. Okay. This usually is written like this, and so this is the weight, or which are called as the, these are the importance weights. Okay. So, this is a ratio of the old probability distribution, which is uniform or which is taken from another distribution, and q x is a new distribution. So, it is the ratio of that, and so we have to normalize the weights such that sum over I equal to 1 to n w x I should become equal to 1, and in which case we can write down this integral as simply 1 over n sum over I equal to 1 to n. I hope this is visible. It is I equal to 1 to n. Let me then rewrite it more carefully. So, I equal to 1 to n, and you have a w x I f x I. So, now instead of weighting it by the p which is a probability density function earlier one, we now weight it by the importance weights, and this of course has to be normalized I equal to 1 to n and w x I and so on, and this is equal to 1 over n I equal to 1 to n and w n x I f x I and so on. Okay. Where your w n x I equal to w x I divided by the normalized w x I from 1 to n. Okay. Now, this is the main issue about this, or that this is the main concept that is involved here, is that we have instead of this p x, we have w x, and with w x is derived from this p x with another distribution q x, which seem to fit this better. So, let us see a little more on the variance and so on. Of course, the estimate is biased, because instead of a uniform one, you have taken a bias distribution which fits your problem more closely, but this bias actually vanishes in the asymptotic limit. So, it asymptotically as n tends to infinity. Okay. So, the variance of this thing is given by variance of this q distribution is given by, it is equal to 1 by n f of x p x square, sorry, this is divided by q x, and then one has to take a square of this, and this is square dx minus e for the p one, this is for the p PDF, the original PDF square, so to say, f of x. This is that original thing that we have discussed. So, this variance is for the new one minus the old one, and to reduce the variance, q x should be chosen to match the shape of P x or f x P x. So, what I am trying to say is that Q x is often is proportional to P x. So, in summary, a good importance sampling Q x satisfies certain properties. Q x is greater than 0 whenever f of x is not equal to 0. Okay. Q x should be close to being proportional to, which is what I just said, to f x. And then of course, what is important is that it should be easy to simulate values from Q x. Okay. It should be, as I said earlier, that it should perhaps be easy to simulate values, so that we get a better estimate and things like that for the integral that we are trying to compute. So, there is just one thing that one wants to take care of. So, it says the, let us say, the final comment, or rather this pitfalls of importance sampling. Because we are taking a ratio, you need to be careful about the tails of the distribution of this distribution of Q. Suppose Q has a distribution which is having a normal or a Gaussian distribution, one needs to worry about the tails, even though it is a sort of a slightly improbable situation that it would happen, but the tails of the distribution, the new distribution, that is the importance distribution Q, still matter. Okay. So, how does it matter? So, while Q x may roughly be same shape as f of x, serious difficulties arise if Q x gets much smaller than f x. And why is it a difficulty? Because this importance weights are proportional to the ratio of these. I mean, get smaller than f of x is not the right this thing, get smaller much faster than f of x, and around or among the tails of the distribution. Because in this case, what happens is that for a particular value, of x I, the Monte Carlo estimator which is f x I by q x I. So, maybe actually may become order of magnitude larger than typical values of this. Okay. Rather typical values of q of f x, not q, f of x. Okay. So, these are some of the things. So, basically what I mean to say is that it is very highly improbable that in the tails of the distribution things can these ratio can become much larger than the typical values, then they would start contributing dominantly, which is what is not wanted. So, but these are very improbable situations. Let us see an example of how to use this importance sampling and how importance sampling can improve the approximation for a given integral. So, consider a function f of x equal to 10 exponential minus 2 x minus 5. Okay. And suppose we want to calculate the expected value E f x by two methods. One is, let us call it as a normal sampling, which is what we have been exposed to from the beginning, that is using a uniform distribution, or B, the importance sampling, using a different distribution. And how do we choose the different distribution? We will just come to that. Okay. So, let us look at this normal sampling A. All right. So, we will use a uniform distribution. Let us write that uniform distribution as 0 and 1, which means the mean at 0 and the variance is 1. So, let us write that mean equal to 0 and variance equal to 1. So, we want to compute the integral. Uh, 0 to 10 exponential minus 2 x mod x minus 5 dx. Okay. So, a regular approach would be to generate xi from uniform 0 1 distribution. Here, because we have taken it to 0 10, because this integral has an approximate value of 1, we could do that. Okay. So, this integral has a value which is close to 1. So, this is this uniform density or the uniform density function. Compute. So, this is 1 and this is compute the sample mean of 10 times f of x I. Okay. So, basically you pick random numbers from this distribution, uniform distribution, which is like this. Okay, so, this is from 0 to 10 and this is 5 say, just to mark this. So, this is your p of x, and so one chooses values at random from this, and then calculate I equal to 1 over n, I equal to 1 to n f of x I to calculate the integral. So, this will give the value of the integral. So, note one thing which will become more clear, that this is the importance sampling with importance function So, W x is equal to nothing but your P x. Okay. So, now let us look at the more important thing, which is called as the importance sampling. All right. So, for doing that, take a note that f x is peaked at x equal to 5 and decays quickly on either side of 5. All right. So, if that is the case, doing or taking a uniform distribution is probably not such a good idea. So, what we can do is that one can take a Gaussian factor which is like exponential minus some alpha x square etcetera, with a peak at 5 and minimal variance, and the variance can be equal to say 1. So, we can write down the integral as so, it is from 0 to 10, and we have this function which is minus 5, and then there is a 1 over 10, and now there is a 1 over 2 pi exponential minus x minus 5 whole square by 2, and in 1 over 2 pi exponential minus x minus 5 whole square over 2 and a dx. See, exactly we have introduced a q below and a q above. So, this is the importance weight. So, this gives the expected value of f of x, w of x with x chosen from not from a uniform distribution, but from a normal distribution with mean at 5 and variance equal to 1. Remember that we have used this language or terminology for denoting a normal distribution, with the first of the argument that represents the mean and the second one represents the variance. So, here we identify P of x equal to 1 over 10, Q of x is equal to the normal distribution, which is 5 1, and W of x which is equal to a root over 2 pi exponential minus x minus 5 whole square by 2 divided by 10, and this is nothing but equal to p x over q x. Okay. So, this, please go back and see the definition, this is exactly what we have done. So, instead of a constant distribution which is like 1 over 10, we have now taken a distribution which is normal with variance and a mean that is given here. Okay. So, W x is the importance function here, let me write that here itself. Or you can call it the importance weight and so on. So, let me box this. So, if that is the case, then the integral is more compactly written as zero to 10 exponential of minus 2 mod x minus 5 root over 2 pi exponential x minus 5 whole square by 2 and 1 by root over 2 pi exponential minus x minus 5 whole square by 2 dx. Okay. So, this is the original f x and this is the density being integrated, or so this density corresponding to the n 5 1, the normal distribution. So, let us plot this thing to have a more intuitive understanding. So, this plot of the integrand from a and b. So, let us take a different color for. So, this is the uniform distribution all throughout, which is same. So, this and this is equal to the distribution. Okay. And so, we are showing it, I mean it is slightly it should have been slightly more rounded, but what is important here is the following. So, you have so this is like 2 and a 4 and and maybe a, well let me just do it. So, this is 5. Okay. So, this is say 6 and this is say 4 and so on, and this is of course, this is like a 0.2, 0.4, 0.6, these are normalized 0.8 and 1, and so this is so this is corresponding to the uniform, the normal sampling, and this corresponds to the importance sampling. You can see that this importance sampling is likely to give better results, because this is peaked at 5 where the function peaks it. So, you have another distribution from which you want to take, and this distribution is better than the uniform distribution. So, you see that the value of the function falls off quickly on either side of 5. The uniform distribution does not know anything about it, whereas the importance distribution that knows that this is it falls off quickly and so on. So, the uniform distribution has PDF equal to 1 over 10, and the importance sampling equal to this exponential minus 2 x minus 5 into root over 2 pi exponential x minus 5 whole square over 2. Okay. So, this is it gives you an intuitive way to understand why the importance sampling gives much more accurate results for this. It is a very important thing in the study of Monte Carlo, where we should always weight it by an importance function rather than by doing a normal sampling, especially for complicated integrals. This makes much more, or rather provides much better estimate of the integral.